Hello everyone, so let's look at our newest theme, and it's the theme on chemical kinetics. So kinetics is the study of the speed of reactions. So basically the question of how fast do chemical reactions actually proceed. So we're going to use a lot of analogies or ideas of how fast or how quick do things really proceed, and actually the idea of what is the rate of a reaction. So exactly what is the rate at which a reaction proceeds, and how can we monitor that, and what kind of units can we use to look at that. So just some basic things that we can perhaps get ahead of is the moment you start thinking of the rate of something, you associate that with the speed of something, right? So a rate is a speed, and speed is always delivered in something like a kilometer per hour and other things that we can start to look at. We can also break down the study of rate or how quickly reactions happen on two levels. So at the macroscopic level, so meaning just observing chemical reactions, I say macroscopic level, we look at determining these reaction rates. So meaning how quickly do reactions actually occur, and we look at factors like temperature, reaction concentration, and how that influences literally how quickly a reaction proceeds. So meaning how fast the chemical reaction occurs. But on a more microscopic level, something that we won't necessarily look at, it is concerned about what is the reaction mechanism. So meaning specifically, what are the steps involved in a chemical reaction. So that's something we won't necessarily look at, but just so that you know, we'll focus more on the idea of how quickly does a chemical reaction happen, and how do things like the temperature, like the concentration, influence how quickly a chemical reaction takes place. And that is based, or our idea of chemical reactions is based on a so-called collision model. So we're going to look at that. And the collision model is, it makes inherent sense. For a reaction to take place, two species need to collide, and they probably need to have some orientation, and this collision needs to have sufficient energy for the reaction to take place, and that of course is going to have some influence on how quickly the reaction takes place, because if those three factors or three conditions aren't met, then your reaction doesn't actually take place. So we'll look at how that is influenced, or that can dictate your reaction. So of course that links to the idea of energy, or the average kinetic energy of your molecules, meaning if you, for example, have the average kinetic energy of your molecules is higher, how does that influence the overall reaction rate? And the point being that the things that we can, so we've already alluded to it, what are the things that we can then influence or control to assist with a reaction? And that of course is, so the concentrations, we'll speak a lot about that, the temperature of a reaction, and things called catalysts. So the concentration one might seem quite obvious. If you have more of a species, then your reaction is, there's going to be a higher rate associated with your reaction, because there's more molecules to react with. So you'll have a higher rate of reaction. More product will form because you have more reactants to react. If you increase the temperature, there's more average kinetic energy. So your molecules have more energy, there's more energy in the reaction, hence there's a higher rate associated with it. And then this thing called catalyst. Now catalyst we'll look at a bit later, but these essentially are things that lower the activation energy required, or the energy required in a reaction, and they allow us to increase the rate of a chemical reaction. But these are all aspects that we will be looking at in this theme. Alright, so that's enough of the prelude, so to speak. So you're probably burning to ask what is a rate? What is a reaction rate specifically? But let's start it a little bit back. What is a rate? And I've mentioned speed a couple of times. So if you think about if you're driving a car, you would say, well, the speed of your car is measured in kilometers per hour, right? And you would get that from saying it's the distance you drive, so the change in your distance divided by the change in time. And that would give you the kilometers per hour, say. So in other words, the distance, kilometers per hour, the time unit. And it would be the same for reactions. We define the rate of a reaction in the same manner. So the rate of a reaction, we will define it as the change in the concentration, so meaning it's the change in a measurable unit that we have per change in time. And if we write that out symbolically for ourselves, it will always be written as the change in the concentration of whatever species we're looking at divided by the change in time. Alright, and what are the units then of this? That means the unit of rate of reaction must be in molar per time. Alright, so that means how many molar, so the rate of reaction is how much molar is there being consumed or formed per time. So let's say, for example, it's 10 molar per second. Then it means this reaction is, say, forming 10 molar of a species every second, right? That's a kind of ridiculous value, but you get the point, right? So every second, 10 molar, and 10 molar is a concentration unit, right? So it gives you an indication of how much species is forming every second. Notice, however, that you wouldn't necessarily ever write here a value like minus 60 kilometers per hour, right? You'll always write a positive value. So you'll always say 60 kilometers per hour. So meaning your speed is always going to be something positive. So, and that is exactly the same for rate of reaction. So your rate of reaction needs to be a positive quantity. And that's an important point to remember, because if you think about it, your reactants are things that are consumed during a reaction. And what will the change be of the concentration of a reactant versus what is the change in concentration of a product? The change of a reactant, so change of a reactant in a reaction, reactant, is going to be negative, right? The change in the concentration of a product is going to be positive, right? And if the rate always needs to be positive, that means we need to do something here about the sign and the way that we calculate the rate of a reaction, depending on whether or not we're looking at the change in concentration of reactants and products. Okay, so that's just a little note that you might want to make for yourself. But we will look at that like just now. So how do we calculate the rate of a reaction? So we can look at this in the same way that we would calculate the average speed of a car. So in terms of average speed, so you would usually say, so let's say you drove 30 kilometers in 2 hours. You would say the distance you drove, 30 kilometers, divided by the time. So in this case, you would do exactly the same to get the rate of your chemical reaction. What you need is the time taken for the chemical reaction, and you need the change in the concentration. And that will give you what we call the average concentration, or the average rate of reaction. We're also going to look at something called an instantaneous rate, but for now we'll focus on the average rate. All right, so let's consider a general reaction where A gives B. So A is our reactant, so reactant, and B is of course our product. Alright, and what will happen if we start with 1 molar of A and let it decompose? What do you expect to see if you plot a graph of concentration of A versus time? What do you think is going to happen? What should happen with the concentration of A over time if it decomposes, right? You should expect to see less A over time. That is something that you should inherently see. What's going to happen with the concentration of B over time? B's concentration should increase, right? So let's go ahead and plot that. So I'm just going to say here we have concentration on the y-axis, we have time on the x-axis, and here is, well, 1 molar, just for reference sake. And for A, we should expect to see some sort of decrease, and eventually it should go to 0. Funnily enough, this is decomposition, so it's something called the first order reaction, but you don't know that yet. We'll look at that later. And what happens with B? So, right, A, we start at 1 and eventually it will go to 0, right? Because it's the reactant, it's used up in the reaction. So eventually we'll go to 1 over time. And B, at the start of the reaction, how much B do we have? Well, we have 0 B, there's nothing of B. And eventually, because this is a 1-to-1 reaction, right? 1A gives 1B. It means B is going to start forming, and eventually we're going to start seeing a plateau where we see that. It gets too complex to talk about equilibrium and all that for now, so I'm just going to leave it at that. And you're going to see a plateau, right? We're going to assume it goes to, if A goes to 0, then it means B goes to 1 molar, right? Because all of A is going to be converted to all of B. Okay, so if that's the case, then this is what we see. We have nothing of B at the start, and all of A is converted to B, and that means the concentration of B needs to end up here at this plateau of 1 molar eventually, sometime when A is eventually 0. Okay, and that's what you expect to see. Now, how does that really help us with anything? So perhaps I just want to make some notes here for ourselves. So we see the concentration of our reactant, right? So, or maybe let's write it out. The concentration of our reactant it decreases over time. And the concentration of our product it increases over time. And then in principle, I mean, that applies to all reactions, right? So now the question is, how do we calculate the rate of the reaction? What is the rate of the reaction? So we define to calculate the rate of reaction to say it's the change in concentration over the change in time. So now, in terms of the product, the rate of reaction, this needs to be a positive quantity. And the rate of the reaction in terms of the product would be whatever is the change in the concentration of B divided by the change in the concentration of time. And you can see if no matter what the points are, so let's just take a little different color here. So if I take this point here and I take this point here, and I actually just wanted to get that right. So this is going to give me time 1, time 2, and this is going to give me concentration of B at time 1. This gives me concentration of B at time 2. So then to calculate the average rate of this, I then say, right, it is the concentration of B at time 2 minus, should take away that delta there, it is the concentration of B at time 2 minus the concentration of B at time 1 divided by time 2 minus time 1. And what do you notice about the slope of this line? I know the line doesn't go through the point there, but you know it will go through the points. What do you notice about that slope? It's a positive slope, right? Because the product concentration is increasing, right? As it should. The product concentration increases over time. And hence that will give us the rate of the reaction. Okay, in molar per time. And that is exactly what we expect to see. What happens if we do the same thing for the reactant concentration? So meaning we can take two arbitrary points here. So meaning, again, you can take 2 points on this graph and draw your line. So meaning this is going to be concentration A. This is now, I'm going to just call them T1 and T2 again, because this is just for A. T1 and A at T2. What is the slope of this line? This is of course a negative slope. So meaning, if you look at this change, so meaning the change in A divided by the change in T, and if you write that out as A at T2 minus A at T1 divided by T2 minus T1. This value here, this A delta A, that's going to be a negative value, right? Because you have a smaller value, which is this value, minus a larger value there. So to correct for that, so that we still get a positive rate, what we introduce is, we introduce a negative in front of here. And that is whenever we're working with the reactants. Okay, so that is how we calculate the average rate of a reaction. Then you've now seen it visually as well. So you take the change in the concentration of whatever species you're looking at divided by the time, and you take 2 points on a graph, and you can do that. And if you're working with the reactants, you must remember to include a negative sign. If you have the products, you can keep it positive, because the slope of the reactants will be positive. The slope of the reactants are negative. Sorry, the slope of the products are positive. The slope of the reactants are negative, right? And that's hence why you need to correct for that. All right, so that's what I have here. If you're calculating the average rate, so remember this is an average because you take 2 points on your graph, then you can say the rate of decomposition, just because, I mean, it was a decomposition, but you can write the rate of the reaction is negative the change in A over the change in time. So formally it's negative delta A, concentration of A over delta T. And why? Because A is a reactant. We can also write it as, it's going to be positive change in B over change in T. Where, in a general sense, you remember that delta means the final value minus the initial value. And because for a reactant this is negative, that is why we take the negative for reactants, because a rate is always expressed as a positive quantity. Okay, so I hope I've convinced you of that point and why we must take the positive value. Well, I must introduce the negative to get a positive value. One other thing that we sometimes are interested in, and this will be important for when we look at something called an integrated rate law, etc., is something called an instantaneous rate. So for these calculations, right, you agree we need 2 time units for each of these, right? We needed 2 times, and then we took the average. So we said, what is the concentration at T1? What is their concentration at T2? We said this thing minus that thing, this divided by time minus time. But what if, let's say for example, you wanted to know what is the rate of the reaction at? So the question becomes, what is the rate of reaction at? Well, that's a very bad at. I'm not happy with that. What is the rate of reaction at T equals 0? So meaning you want to know what is the rate at a specific time. Right, so meaning it's just a point. You need to know what the rate is at a point. So you can't use 2 points. You need to know what the rate is at a point. And the answer becomes, well, you can use then the idea of a tangent line. So you can draw a tangent to the line, and you can calculate the slope of this tangent line. So the slope of the tangent. And that will give you the instantaneous rate, or something called the instantaneous rate. So that is, but it's a different concept. And that is linked to what we call infinite, or what you will look at later on in the concentration time curves to particularly determine things. Also look at some other points. All right, but for now, at least you have the basic idea of where does the rate come from and how to determine it from its concentration and time data. All right, so that is what I wanted to do in this video. In the next video, we'll go over how does it now change, or how does the situation change if you, for example, introduce the idea of stoichiometry. So let's say you had a reaction where 2A gave B. How does that change your rate of reaction? Okay. Thank you for watching.